Let's talk about area in polar coordinates. So area in polar coordinates. Area is an integral, as you might expect. The integration may not be the most difficult part, though. So area is defined as 1/2 times the integral, and a lot of times they put like alpha and beta here. This is angle alpha, angle beta. And we put our polar function, f of theta, and we square it. Put d theta. So it's kind of like the area of a sector, that type of a formula. Once in a while, this is described instead of with the function as just r, because r equals f of theta, so r squared d theta. Now notice we've got a different function here than we do here, so you've got to be concerned about that. There are some rules about this. You've got to have 0 is less than beta minus alpha, so beta's got to be bigger than alpha, and they've got to be less than or equal to 2 pi. Their difference has to be. The other thing is you've got to make sure that this is going to be a function that's always positive or always negative where you do this. So make sure that these have the same sign. Now we're going to work on that, but if it dips into the positive and then into the negative, then it kind of cancels itself out, like they did when you did area above and below an x-axis. So we've got to be concerned about that. Now here's my example that I'm going to use. This example has f of theta is equal to 1 plus 2 cosine theta. Now this is a limacon with an inner loop. We know that because if we take A over B, this is A and this is B, and kind of a standard technique. So 1 over 2 is less than 1. So that tells us we've got an inner loop. So you can actually judge that. Now the question that is posed for this is for us to find the area between the inner and outer loops. Now what do I mean by that? Well, let me put the calculator up here. I've got this thing graphed. Here's my graph. You might notice, here's my function, 1 plus 2 cosine theta. And so I have this graphed. Now, if I want to go between the inner and the outer loop, what I've got to do is I've got to get this big area in here, but not the loop. So how do I find my bounds? I think the bounds are the most difficult part. The integral is not really the most difficult part. So let's trace this thing, and I'm really thankful for calculators here, but let's trace this thing and figure out what we want to do. For one thing, you might notice that it's symmetric, top and bottom, or it looks like top and bottom. So if I just do the top, then I can double it and I will have a value for the bottom. So that's kind of where I'm going to go. Now, when I trace, it's going to start at 0 because my window is set up to go from, my theta values are 0 to 2 pi. So it's going to start at 0. So if I hit trace, it's going to start at 0. Now this is angle 0, so it starts there. And if I start going forward, which I'm going to do here, notice how it goes like this, okay? Then I go to there. Now that's not exactly y is 0, it's pretty close, you might notice. But what is that value? What is that value? Well, let's see. So my example is right here. I need to know where it has a value where it's at the origin. That's at the origin. So that would be where the radius is 0. So 0 equals 1 plus 2 cosine theta. That is minus 1/2 equals cosine theta. Well, where is the cosine equal to minus 1/2? Reference angle, pi over 6, negative. So quadrant 2, quadrant 3. The answers for theta are 5 pi over 6, that's pi over 6 in quadrant 2, reference angle in quadrant 2, and then 7 pi over 6. Now let me check those out, show you this. So if I put 5 pi, so 5 pi divided by 6, I hit enter, right there. Whoops, 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 whoops. I didn't do it right, did I? Let me try again. 5 pi, so 5 pi, and then I've got to divide by 6. I have got the wrong thing. Who knows, man?